In this video, I'm going to look at the rotational analog of force, which is called torque. And once we understand torque, we'll be able to write down Newton's second law in rotational form. We'll be able to calculate how forces cause angular acceleration in rotating systems. Let's say I have some wheel that's free to rotate around this center of rotation here, the little dot in the middle. And I'm going to apply a force to this wheel. I'm just going to apply this force to this point over here, and I'm going to apply the force at some angle like this. So I apply a force over here, and this point here is some distance r from the center of the wheel. Okay. So when I apply this force, well, I can see that this force is going to make the wheel want to rotate counterclockwise like this. So this wheel is going to rotate through some little infinitesimal angle. I'll call that little infinitesimal angle d theta. If this wheel rotates through d theta, then this point here is going to just go this little distance here, which I can call dr. And using what we know about circles, if this rotates d theta, this little distance dr is going to equal d theta times the radius r here of the circle. That is how far away this force is applied from the center of rotation of this wheel. Okay. So now what I'm going to do is I'm going to say, in the process of F acting on this this wheel here, it rotates the wheel through this little angle d theta. This moves this point through this little distance dr, so it does a little bit of work. I'll call that little bit of work dw. Well, dw is going to equal F, the force, dotted with this displacement vector dr. Now, the dot product of this force with this displacement vector, I can write as, well, I have to break this force up into two components. I'm going to break it up into these components. I'm going to call this component F parallel, because that's the component that is parallel to R. I'm going to call this component here F perpendicular. Now, the only component that does work as I rotate the wheel in this direction is this F perpendicular component. When I take the dot product, only the component parallel to the displacement, which is perpendicular to the radial direction, does work. So I can write this little bit of work here. I'll call this F perpendicular times dr. Magnitude of F perpendicular times magnitude of dr. Now, if I wanted to calculate what F perpendicular was, I would need to know this angle theta here that F makes with the radial direction. This radial direction is this direction that goes from the center of rotation here to the point where F acts. And I would find that F perpendicular equals F sine theta. I'm just going to keep writing this F perpendicular for now, but we'll come back to this a little later. Okay, well, I can write this dr here. I already said dr equals r times d theta. So I'm going to write this as F perpendicular times r times the little angle d theta we rotated this wheel through. All right, now I'm going to rewrite this a little bit. Divide both sides by d theta. I get dw d theta. That's the little amount of work that this force does as we rotate it through a little angle d theta, just equals F perpendicular times r. Well, the work energy theorem tells us that this work that we do on this wheel increases the kinetic energy. The amount of work we do is equal to the change in kinetic energy. So dw d theta just equals the change in kinetic energy, dk d theta. And the kinetic energy for this wheel is going to be 1/2. The kinetic energy k is 1/2. Let me write it down here. K equals 1/2 I omega squared. So dk d theta equals d by d theta of 1/2 I omega squared, like that. Okay, so now I need to take the derivative of this kinetic energy expression. So I have, once again, F perpendicular times R equals, well, I is a constant, 1/2 is a constant, so I can pull those out. 1/2 I times the derivative of omega squared with respect to theta. Well, I have to apply the chain rule here, so I get d. First of all, I take the derivative of omega squared with respect to omega, which is just 2 omega. And then the chain rule says I have to multiply this by d omega d theta. All right, so here I can see, well, this 1/2 cancels this 2 here. Now I have d omega d theta. Well, that's kind of a weird thing. What is the derivative of the angular velocity with respect to the angle? And what I can do is write this as, now it's I times omega. I can break d omega d theta up into d omega dt times dt d theta. Okay, d omega dt times dt d theta. Well, d omega dt, I know what that is. That's just the angular acceleration alpha. dt d theta, well, that's kind of weird. What's the derivative of time with respect to theta? But remember, d theta dt equals omega. So that means dt d theta equals 1 over d theta dt, which equals 1 over omega. So this here, dt d theta, is just 1 over the angular velocity omega. Well, this 1 over omega here cancels this omega here. And I end up with this really simple expression. F perpendicular times R equals I times alpha. So it says that if I apply a force with a perpendicular component, F perpendicular, that is a component that is perpendicular to the radial direction, F perpendicular, I multiply that by the distance I apply that force from the center of rotation. This equals I times the angular acceleration A. Well, this looks kind of like F equals ma, right? I is the rotational equivalent of m, and alpha is the rotational equivalent of A. So this F perpendicular times R must be the rotational equivalent of F. We call this quantity, F perpendicular times R, the torque. Use the symbol tau for torque. And our equation becomes torque equals I alpha. The torque applied to this wheel equals the moment of inertia I times the angular acceleration alpha. This is Newton's second law. Newton's second law for rotations. It's just Newton's second law describing how forces which create torques generate angular acceleration. So this quantity, torque, tau, which equals F perpendicular times R, remember I said that F perpendicular equals F sine theta, where theta is the angle between the direction of R and the direction of F. So I can write this as F times R times sine theta. Well, it turns out we have a quantity that gives us this exact expression, a way of multiplying two vectors together that gives us a third vector whose magnitude is the product of the two vector magnitudes times the sine of the angle between them. That quantity is called the cross product. The cross product we write as with an x, a little cross here. So A cross B equals the magnitude of A times the magnitude of B times the sine of the angle between A and B. I can figure out the cross product if I know the x, y, and z components of A and B using this determinant formula here. A cross B equals, I do a 3 by 3 determinant of I hat, j hat, k hat, ax, ay, az, bx, by, bz. And that gives me this whole collection, this whole complicated expression here for the x, y, and z components of the cross product in terms of the x, y, and z components of the two vectors that I'm inputting. But an easier formula to use, if I know the magnitude and the angle between the two vectors, is just this A times B times sine theta. The thing that's a little confusing about the cross product is that the cross product is itself a vector. So the direction of this cross product is kind of weird. This cross product is a vector. It doesn't point in the same direction as A. It doesn't point in the same direction as B. It actually points perpendicular to both A and B. And if you think about it, if I take any two vectors, those two vectors will lie in a plane, and the direction perpendicular to those two vectors there are two possible directions that are perpendicular to those two vectors. There's up and down with respect to that plane that they make. And in order to figure out the direction of this cross product, I have to use the right hand rule, where I have a little diagram here showing it. I point my index finger in the direction of A, middle finger in the direction of B, and my thumb will point in the direction of the cross product. Okay, we'll come back to this a little bit later, but this direction for the cross product is kind of weird, and it has some interesting consequences when we're talking about torque. So, the torque is what we call the twisting action of the force. It's how much a force makes an object rotate. And we define this torque using the cross product. The torque tau equals the cross product of the vector r and the vector f. This vector r is a vector that goes from the center of rotation of our object, so whatever point the object can pivot around, whether it's the center of a wheel or a place where some rod is anchored that can swing around. This vector r goes from here to the point where the force is being applied. It could be applied at the end, it could be applied in the middle. R goes from center of rotation to the place where the force is applied. And that force, in general, will make some angle with this radial direction. So I can find the twisting action of this force, this torque tau, by just taking the cross product of r with f. I can write that in terms of this angle theta here as r times f times sine of theta, where theta is the angle between r and f. I can also write this as r times f perpendicular, where f perpendicular is the component of f that is perpendicular to the radial direction. That's how we defined it when I was deriving Newton's second law for rotations. And I can also write it as r perpendicular times f, where r perpendicular is the vector that is the component of r, I should say, that is perpendicular to the direction of f. I can break r into components parallel and perpendicular to the force vector. R perpendicular is this perpendicular component of r. Okay, so that's how I define this quantity torque. And a torque is the rotational equivalent of a force. Applying a torque results in an angular acceleration according to Newton's second law, which says that alpha, the angular acceleration, equals the net torque divided by the moment of inertia I, where the net torque is just the sum of all the torques acting on an object. So if I have multiple forces acting on an object, I can calculate the torque from each force. I add up all those torques, I get a net torque, I plug that into Newton's second law, and I can find the angular acceleration. Okay, so that's our starting point for understanding torque and angular acceleration. Now, I want to walk you through some conceptual questions to get you really to think about how torque works. A wheel is free to rotate about its axle. That's a line going through the center of the wheel right here. All forces shown below have the same magnitude. Rank the forces shown acting on the wheel in terms of the magnitude of the torque that they apply to the wheel. So F1, F2, F3, F4, they all have the same magnitude. The forces are the same size, but they act at different places. So I want you to rank these forces in terms of the torque that they apply to the wheel. So pause the video, take a moment, think about it, and come back when you think you have an answer. To answer this question, let's look at our formula for torque. Torque equals F perpendicular times R. Well, R is a vector that goes from the center of rotation here to the place where the force is acting. So I've got a few different R's here. I've got R1, that's R for the force F1. I've got R2, that's R for this force F2. I've got R3, that is R for this force F3. And finally, I've got R4. It's R for this force F4. Okay, so those are my R's. So now that you see what the R's are, why don't you take a minute and think about what the answer to this question is. Pause the video, come back when you have an answer. Okay, well, for each of these R's, I need to not only know what R is, each of these forces, to find the torque, I need to not just know what R is, but I also need to know what F perpendicular is. Well, for F1, if I look at F1, all of this force here is perpendicular to R. The force points perpendicular to R1. So the torque here, I'll write it down here, torque 1 equals just R1 times F1. F perpendicular equals the magnitude of F1 at all points perpendicular to R1. For F2, well, this force makes an angle with R2. This is F perpendicular 2 here. It's going to be smaller than F2, right? Not all of F2 points along points perpendicular to R2, just a portion of it, a component of it does. For F3, same idea. F3 is only this component of F3, F3 perpendicular, is perpendicular to R3. And then F4, well, for this one, there is no perpendicular component. F4 points parallel to R4. So F4 perpendicular is just 0. Okay, so tau 1 is R1 F1. Tau 2 equals R2 F2 perpendicular. Tau 3 equals R3 F3 perpendicular. And tau 4 just equals 0. So I know that tau 4 has to be the smallest. There's no torque from F4. So it's either A or C. Okay, now take another minute and see if you can figure out which of these is it. Is it A or is it C? Okay, well, it's pretty easy to see that tau 1 is going to be the biggest, right? Because all of F is perpendicular to R, and this R is the whole radius of the wheel. So this force is applied as far from the center as it possibly can be. But in both of these, tau 1 is ranked highest, so that doesn't help us much. So the question is tau 2 bigger than tau 3? Or vice versa? Is tau 3 bigger than tau 2? Okay, well, the answer to this is, if we look, F3 and F2 both make about the same angle with their radial vectors R. But F3 has a longer radial vector than F2. Since R3 is greater than R2, it's about twice R2, whereas F2 perpendicular is approximately equal to F3 perpendicular. They point in opposite directions, but they have about the same magnitude. It's pretty clear then that tau 3 has to be greater than tau 2. So our correct answer here is C. Tau 1 is the biggest, followed by tau 3, followed by tau 2, and then tau 4 is 0. Okay, so that is just a quick look at how torque depends on not just how big the force that you apply is, but where you apply it and what angle that force makes with the radial direction. So calculating this torque can be a little bit complicated, but you'll get the hang of it pretty soon. One thing I forgot to mention, I want to point out, this is the Greek letter tau. I call it tau, some people call it ta. It's not a T, it's a tau. It's just got a little curved bottom and a curly top. So try to draw it that way and try to call it tau. Okay, here's another question. A wheel is free to rotate about its axle. The wheel begins at rest and a force F acts on the wheel. What direction does the wheel rotate? Okay, So we apply this force F1 from the previous question. What direction does the wheel rotate? Does it rotate clockwise, counterclockwise, or is it impossible to tell? Pause the video, think about it, come back when you have an answer. All right, well, if I'm applying this force here, it pushes this point up, which is going to cause the wheel to rotate clockwise. It's pretty easy to see that if I apply this force over here, the wheel's going to rotate clockwise. Now, if I took this force and applied it on the opposite side of the wheel would rotate counterclockwise. So the magnitude of the torque depends on where I apply the force, and the direction that the wheel rotates under the influence of the torque depends on where I apply the force. Okay, so F pointing up over here causes the wheel to rotate clockwise around like this. Okay, here's another question. Same thing. Wheel is free to rotate about its axle. Wheel begins at rest and the force F acts on the wheel. What direction does the torque vector point? Does it point up, to the left, into the board, or out of the board? So take a minute, think about this question, pause the video, and come back when you think you have an answer. Okay, well, let's remember that this torque is a vector, tau. This vector is defined by R cross F. It's the cross product of the radial vector crossed with the force vector. And this radial vector is the vector that points from the center of rotation to the place where the force acts. Okay. So we have to take the cross product of R with this force vector F. So take a minute, think about what direction that cross product points, and then come back when you think you have an answer. Well, right away we know that this vector tau has to be perpendicular to the vector r and to the vector f. So it can't point along the direction of f, so A is right out, and it can't point along the direction of r, so left is right out, B. So it's got to either be into the board, that is into this screen, or out of this screen. And remember that the way you have to calculate this is to use the right hand rule. So you point your index finger in the direction of R, point your middle finger in the direction of F, and see which direction your thumb points. So try this and come back when you think you have an answer. So let's try this. Index finger in the direction of R, middle finger in the direction of F. My thumb, you can see here, points into the screen, into the board here. So the direction of this torque cross product vector is into the screen. Try it yourself and you'll see the same thing. So the right answer here is C, into the board. Now, I don't really like contorting my hand like this, so I have a different way of doing the right hand rule, which is I point my fingers in the direction of R. They're pointing this way, then I curl them in the direction of F, and then my thumb points in the direction of the cross product. Okay. So we can see that this cross product points in the direction C into the board. Now we can draw the direction into the board like this. I can draw a vector, I can draw a circle with a little X in the middle. That is a vector that points into the board. Now this is weird. What does it mean that the torque points into the board? Well, I'll show you in just a second. So vector quantities like net torque, angular acceleration, and angular velocity all point along the axis of rotation. They don't point in the direction that some point on a rotating object moves in. They point along the axis of rotation. That is, they point along the direction this thing rotates around. So here I've got a diagram with a little rotating wheel. If I apply a force F with a radial vector r, it creates a torque that points in the direction of the red arrow. And I can see what a torque in that direction means by pointing my thumb along the direction of that red arrow. So just like in the diagram, thumb points this way. That means my fingers are going to curl in the direction that we rotate. So in general, if I have a torque that points in any direction, I can point my thumb in that direction and my fingers will curl in the direction that that torque will cause something to rotate. Or if I know that my wheel is rotating, say this way, I can curl my fingers in that direction and my thumb will point along the direction of the torque, the angular acceleration, and the angular velocity. Now, you have to do all of this with your right hand. doesn't work with your left hand. So when you're thinking about the directions of torques and angular velocities and so on, put your left hand behind your back, just use your right hand to figure it out. This is a little bit confusing, and for the most part, we're not going to worry too much about this vector direction of torque, but we are going to come back and revisit it when we look at angular momentum and gyroscopes.